Here's something about delta-matroid. This is going to be first 1 hour talk.
Yeah, thank you for the introduction and thank you for the opportunity to give a talk here. Yeah, and today's topic is gamma graphic delta-matroid and their applications. And, yeah, my name is Donggyu Kim, as you know. And this is joint work with Deok-sang Lee and Sang-il Eum. Okay, let's start. So I think I need to define delta-matroid first. A delta-matroid is a set system. Set system E, F. Here E is a finite set and F is a family of subsets of E, satisfying some two conditions, two axioms. First, F is non-empty, and the second one is for all members A and B in calligraph F, and all A in the symmetric difference A and B, there is a B in symmetric difference A and B, such that A symmetric difference AB is also a member of F. We call this axiom the symmetric exchange axiom because we can find many symmetric difference here. So, and we also call each member of the F a feasible set of the delta-matroid M. So it looks quite difficult. So when I first learned this concept, it looks very difficult, but this is a kind of generalization concept of the delta-matroid. So if you remember the definition of the delta-matroid, if you remember the definition of the matroid in the sense of the basis, so we can recall its definition. So a set system M is a matroid if E, B is a matroid if B is a non-empty and is satisfying some basis exchange axiom. So for all A and B, A in A minus B, there is a B in B minus A such that A minus B plus B is also a basis. So we know that we call this a basis exchange axiom, and the basis a symmetric exchange axiom is a kind of relaxation of the basis exchange axiom. So every matroid is an example of the delta-matroid. Okay, so let's see another example of the delta-matroid. So we can define a delta-matroid from the matrices. So let F be a field and A be an E by E symmetric and skew-symmetric matrix over the field. And let's define FA, calligraph FA, be the family of subsets of E, satisfying the following. So determinant of AX, here AX means the X by X principal submatrix of the A. And determinant of AX is non-zero. And we, here in this talk, we assume that the determinant of 0 by 0 matrix is 1. So FA always contains an empty set. Okay, and in 1988, Bouchet proved the following. So a set system E, calligraph FA is a delta-matroid. And we say a delta-matroid M is representable over the field F if it can be expressed as follows. So E, FA twisting X. So I'm not defining this notation yet, but yeah, I will define it in the next slide. So this is the one of two operations to define the minors of the delta-matroid. So let's see. So M is a delta-matroid and X is a subset of the ground set, and we define twisting. M twisting X is a set system E, Fx, where Fx is the family of A symmetric difference X, where A is a feasible set of M. I mean, A is also just a member of the F. And we can define deletion very naturally. So M deleting X is a set system E, X, E minus X, F minus X, where F minus X is just a set of the feasible set which does not intersect with X. And here we assume that some technical reason we assume that this is non-empty. And if you can remember the definition of the delta-matroid well, then you can easily show that these both M twisting X and M deleting X are delta-matroids. So we define a delta-matroid n is a minor of delta-matroid m if it can be expressed as m twisting x deleting y. Okay. So let's see another example. Delta-matroids from the graph G and the vertex T. So let GGT is a set system whose ground set is the edge set of G, and F is the set of subsets of F E such that satisfying some following conditions. So the first one is the spanning subgroup. The spanning subgroup VG, F is a forest, and the second one is for each component of the spanning subgroup is satisfying one of the following conditions. The first one is the intersection of VC and T is odd, and the second one is the intersection is empty and the induced subgroup of G induced by VC is a component of G. The second one is to deal with some exceptional case. So it is enough to only the focus on the first one. So remember that it is collection of F satisfying VG, F is a forest, and the intersection of VC, here C is a component of VG, F, is VC intersection T is odd. Okay? So yeah, I know that the definition is quite complicated. So is there anyone can understand this? Maybe it is hard. Yeah, so let's see an example. So if you consider this graph, G, and T is here two red marked vertices. Okay, this is G and this and these are T. Then if you consider on edge set A, B, C, then this is just a cycle. So this is not a forest, so this is not the member of the calligraph F. And if you consider D, C, A here, it is hard to control, A, C, D, then this is a path of length 3. So this is a forest. However, since it contains two red vertices, so it does not satisfy the first condition, this. Therefore, it is also not a member of the calligraph F. However, if you consider AD, edge set AD, then it has two components, this, and both satisfy the first condition because each component contains one red vertex. Okay? So this is the definition of the GGT. And proof that this is a delta-matroid. This set system is a delta-matroid, and we say a delta-matroid is a graphic if it can be expressed as a GGT twisting X. Here X is a subset of VG. And also this class, the class of the graphic delta-matroid is minor closed. And let's go back to the definition of the GGT. Yeah. And there is some simple way to define some another way. So this is a vertex set, and if you consider, if you replace T by gamma, here gamma is the map from the VG to the Z2. Z2 is just 0, 1 group. And if you consider like, so V is in T if and only if gamma V is 1. Then there is some natural correspondence between T and gamma, and also you can easily check that these two conditions are equivalent to the previous one. The VC intersection T is odd, each side is odd if and only if the summation of gamma value over all V in VC is 1. And also this is zero map if and only if this is empty set. Okay. So one can naturally ask that, can you generalize this concept for the general abelian group gamma rather than the Z2? So the answer is yes. So this is just copy of everything except some gamma. So here gamma is Vg to the gamma, and we say a pair G gamma is a gamma labeled graph if this is a pair of graph G and gamma. And yeah, everything except these are same. So here small gamma is Vg to the gamma rather than the G Z2, and we choose the summation of gamma value on the component is non-zero. Okay, so for example, if you consider this and if you consider a singleton A, then it Vg, F has a three components, this and this one vertex and this one vertex. But however, the summation of 1 and 2 is 0, so it does not satisfy this condition. So this is not the member of the Kelly graph F. Yeah. Okay. And we prove some similar results. The first one is for any gamma labeled graph G gamma, a set system G gamma is a delta-matroid. And the second one is minor closeness. So if you define M, a delta-matroid M is a gamma graphic when M is equal to GG gamma twisting X, then the class of gamma graphic delta-matroid is minor closed. And let's look more details about the minor closeness. So I will define some minors of the gamma labeled graph, and also I already defined the minors of the delta-matroid. So I will compare between the minors of gamma labeled graph and the minors of the graphic delta-matroid. So first I will define the minors of gamma labeled graph. So this is easy. So just let B is the vertex B and E is a non-loop edge. And deleting is just deleting, and deleting V is naturally defined, and also deleting E is defined very simply. And contracting is also simple, but you need to define a new map because the vertex set is now different. So gamma prime is defined as follows. So if W is the new vertex by contracting E, if W is the new vertex created by contracting E, then we assign this as a gamma X plus gamma Y, where X and Y are edges of E, and the vertices of E. And otherwise, we preserve the gamma value. So for example, if this is the original example, if we contracting C, then you can get this. Okay, then what we prove is for a G gamma or gamma labeled graph and gamma graphic delta-matroid M satisfying this, which expressed as this, then it's satisfying the following. The first one is if we have some minors of the gamma labeled graph, then corresponding gamma graphic delta-matroid is also a minor of the M. Okay. And the second one is if we have some minor of some gamma graphic delta-matroid M, then it is also gamma graphic delta-matroid, and moreover, it can be expressed as this. So here original M is this, and M prime is a minor of M. Then M prime is expressed as G prime gamma prime X twisting X prime, and where G prime gamma prime is a minor of the G gamma. Yeah.
You don't even allow loops to be deleted?
Yeah, that's a good point. I forgot it. For the loop case, deleting is the same, and for the contracting case, we just delete. Yeah, I forgot it. Yeah, thank you. Yeah. Okay. So is it okay to this part? Yeah. And the second result, the next result is about motivated by this question. So when is gamma graphic delta matroid is graphic. So actually there is a spoiler. Even gamma graphic delta matroid is set to graphic. So now I need to define what is an even delta matroid. So this is a very simple subclass of the delta matroid. So a delta matroid is even if and only if all its feasible set has the same cardinality. So if I'm sorry, not same cardinality, same parity. Yeah, thank you. Yeah, so yeah, for if we have f and f prime, then this. And for example, every matroid is an even delta matroid because all bases are equicardinal. And the simplest non-even delta matroid is this, a matroid consisting of empty set and a singleton A. Yeah, of course, the cardinality is different by one. Yeah, and also unproved that every graphic delta matroid, which is same with the Z2 graphic, is even. And we proved that a graphic delta matroid is even if and only if it is graphic. So for example, if you consider this graph, this delta matroid, then this is a Z3 graphic. Because if you consider this G and label this, then empty set is feasible set because feasible set of the G gamma because both are non-zero. And if we consider this H itself, then this is also the feasible set because 1 plus 1 is 2, but 2 is not the zero in the Z3. However, this does not hold for the Z2, of course. And actually, these similar things hold for every gamma which is not Z2. And our third main result is about the algorithmic application. So let's consider this problem. So the input is the gamma labeled graph G gamma, and also another input is a weight on the edge set W. And the problem is we want to find a maximum feasible set of G gamma. Okay. And we proved that this problem can be solved in polynomial time. Moreover, it can be proved greedily. One example is some very artificial one, but one example is this. So let's fix the gamma here. So gamma is zk, and we have some unknown g, but we fix small gamma, the map, as a constant map to 1. Then the feasible set of g gamma is just satisfying the following. So vg, f is a forest, and for each component, which is a tree, satisfying the following. So each size is non-zero, not congruent to 0 modulo k. Yeah, this is an example. So, so this is very similar to the MST, I mean minimum spanning tree problem, but there is some big difference, I think. So, okay. So now I will prove this theorem, and to prove this theorem, the symmetric greedy algorithm is very useful. So symmetric greedy algorithm is very similar to the greedy algorithm for the matroid. We can define the matroid as in terms of the greedy algorithm. So and also Bouchet proved some similar things. So Bouchet proved that following. So a set system E, F, which such that E is a finite set and F is a non-empty, if the following are equivalent, that M is a delta matroid if and only if the symmetric greedy algorithm gives output maximum feasible set for any weight. And yeah, I think I need to explain the symmetric greedy algorithm very simply now. Yeah. So to do that, we need some oracle which answering something about the set system. So we say a set system for a set system E, F, a pair of disjoint subsets X and Y is a separable if there is a member F in calligraph F such that satisfying the following condition. This means that graphically, this means that here is a ground set E, and this is X, this is Y, and there is some F in the member calligraph F satisfying the following. So yeah, graphically, you can understand why we say this is a separable. Okay. So if we have some oracle answering the separability, then we can apply this symmetric greedy algorithm, and Bouchet proved the symmetric. If M is a delta-matroid if and only if always symmetric greedy algorithm gives the best answer. So E is enumerated like this, and enumerated with respect to its absolute value of the weight. And initially, X and Y is empty set, and we will return X after we put each element EI into X or Y. So if the weight is non-negative, then we check the separability of the X union EI, Y. I mean, we want to check that there is a feasible set contains X union EI and which does not intersect Y. If then we update X as X union EI. If there is no, if that it is not separable, then we update Y. And we do similar process when the weight is negative. The weight is negative. We do not want to put it into X because we want to maximize the weight. So we check that the separability of X, Y union EI. And it depends on the answer, we update Y or X. Okay? Actually, you don't need to remember the symmetric greedy algorithm, but what you only remember is separability. So to prove our theorem, so because of the symmetric greedy algorithm, it is enough to show that we can decide whether a pair XY is separable or not in polynomial time. If we can decide it in polynomial time, then by the symmetric greedy algorithm, the problem is solved. And very fortunately, there is some good, necessary, and sufficient condition to checking the separable. So let kappa be the number for gamma labeled graph H and H, eta, let kappa H eta be the number of the components C, such that all each vertex is labeled by 0. Okay? And actually, this is very simple concept. The number of the and we prove that this lemma. So X, Y is separable if and only if this minor of G gamma, contracting X and deleting Y, is each kappa value is the same with the kappa G gamma. Okay, I will not prove this lemma, but yeah. And actually, you can compute kappa very simply by some Breed's first searching algorithm or some anything else, and also contracting and deleting can be done in the polynomial time, of course. So yeah, we can compute this in polynomial time, and it is easy to compare, and so we can check the separability in polynomial time. So this means that this proved this theorem. Okay. And now, yeah, let's move on to our last topic. So about the representations. Maybe local will be interested in this topic, maybe. So yeah, so proved that Z2 graphic delta-matroid is representable over the binary. Every binary field. Every Z2 graphic delta-matroid is representable over GF2. And one can ask that then what is the relation between gamma and F, abelian group gamma and the field F, such that every gamma peak delta-matroid is representable over the field F. And we answer this question, not completely, but almost completely. So for every prime P and integers integer K and L, such that K is at most L, average at peak K graphic delta-matroid is representable over the field of order P to the L. Moreover, this is representable over the field of characteristic P, whose dimension is at least K. Here, dimension means that you can always consider the field of characteristic P as a vector space over the field of order P. Okay, then, and the dimension is the dimension of the vector space. So for example, dimension of GFP vector space GFP to the L over GFP is just L. And we also prove the other direction. So let gamma be a non-trivial finite abelian group and F be a finite field. Then if every gamma graphic delta-matroid is representable over the field F, so if F, then gamma must be isomorphic to ZPK, and F is a field of order P to the L for some prime P and integers K and L. Here we have some weakness about the finiteness. We assume the finite abelian group and finite field, and also there is no relation between K and L here. And actually, I very wonder that can we guarantee that K is at most L like this? Then actually we can characterize all pairs of gamma and F, finite gamma and F, satisfying the following condition. Okay, and now I will prove the first part of our lemma, our theorem. For every prime P and integers K and L, such that K is at most L, average at PK, delta-matroid is representable over GFP to the L. So the first, we do some pre-processing. So M is a gamma graphic delta-matroid, so this is equal to GG gamma twisting X. And first, we may assume that X is empty set because of the definition of the gamma graphic delta-matroid and the representability. And the second one, this is some critical part. We can assume that for every V in the vertex, we can assume that gamma V is non-zero. So, yeah, so let's see some examples. So the given graph is, given gamma labeled graph is this. So this is 1, 1, 0. And we do not want this vertex, and then we uncontract this, so looks like this. Then this is the first one is a minor of the second one, and because of the previous theorem about the minor, we also have this for the corresponding graphic delta-matroid, there is a minor relation. And actually, I didn't mention earlier, but the representability of the delta-matroid is also closed under taking minors. It's like a matroid. So we can assume, because of this, by uncontracting zero vertices, uncontracting vertices which is labeled by zero many times, then we can assume that gamma V is non-zero for every V. Okay, and because we need to prove representability, we need to find some matrix. So let's define some matrix first. So we assign arbitrarily orientation on G, and IG with some signed incident matrix of G defined as follows. So IG, the V, E entry is 1 if E is non-loop and V is ahead of the E, and -1 if it is also non-loop, VE is also non-loop, and V is the tail of the E, and 0 otherwise. Otherwise means that here E is a loop, or there is no incidence relation between V and E. Okay. And the next one is we define some B, which is a diagonal matrix. So let alpha 1 alpha L be the basis of the vector space. We understand the field as a vector space over the GFP. And we define some group homomorphism from the ZPK to the addition structure of the field. Define like this. C1.C2 is the summation of is the linear combination of the alpha I. And this is since K is at most L, this is well defined, and moreover this is injective group homomorphism. Okay, so is it okay to understand the field as a vector space and some additional structure? Only consider the addition operation. And B is defined as follows. So V, V entry is equal to the multiplicative inverse of the phi gamma V. So now we consider the multiplicative operation of the field L, GFP to the L. And since gamma V is non-zero because of the previous assumption, and this is P is the injective map, so P gamma V is non-zero, so this is well defined. And now we define A, the symmetric matrix A, like this. Then I claim that this is the actual matrix representation of our gamma graphic delta-matroid. So this means that it is, in other words, for every F, subset F, the following are equivalent. So for each component C of the VG, F, C is a tree, and the summation of gamma value on VC is non-zero. If and only if we want to show that determinant of the AF, F by F submatrix is non-zero. And I will only show the first direction. Actually, the reverse direction, the proof of the reverse direction is almost same with the downward direction. So yeah. First, let's look some lemmas. First one is about the incident matrix. So G, we can characterize the incident matrix. We can characterize G by some information about the we can characterize the G using some incident matrix. So G is a forest if and only the column vectors of the incident matrix are linearly independent. And second one is if G is a tree, then the number of vertices is just one more than the number of edges. So if we delete one row for any row indexed by a vertex, then it is a square matrix, and moreover, this is determinant of this is plus minus 1. This is easy example using induction. And the second one is Cauchy-Binet formula. And this is some identity of the determinant of the product of two matrices. So, okay. So let M and N be M by Y and Y by M matrices such that satisfying this condition, additional condition, then determinant of product of M and N is satisfying this equality. So we look some Y to make the M and N be a square matrix, and the product of two square matrix and summation of it is the same with this. Okay, then now we can prove our goal. So record that we want to prove this. So we want to prove the determinant of AF is non-zero under this condition. C is 3 and this is non-zero. So let Ci be the all component of Vg, F. Then this A is actually very similar to the adjacency matrix of the graph. So it can be expressed as the block diagonal matrix. Okay, so it is enough to show that determinant of each AEI is non-zero. Then we can show that this is non-zero. Determinant of AF is non-zero. And by the Cauchy-Binet formula, apply it twice, then we can get the first equation. And since B is a diagonal matrix, we can refine it as a second, this one. Okay? And you can remember that each Ci is a tree. So by the previous lemma, this determinant of this is plus minus 1, so its scale is of course 1. So we can get this equality. So record that V B comma B is equal to this gamma V. So determinant of B EI is just equal to the product of among BI, sorry, BI is this. But in here we do not have the V, so we get the inverse of the BVV, which is this. So this looks like this. And we already assumed that this is non-zero. So we can conclude that this determinant of AEI is non-zero. Therefore, the proof of the downward direction, this is complete. Okay, and the backward direction is also same, very similar. So using the first sentence of the lemma, you can easily prove the also backward direction. Okay, then I will finish my talk a little earlier with some open questions. So the first question is there any good application of the maximum rate acyclic gamma non-zero set problem? So I gave you some example, very artificial example, by setting gamma as a ZK, and small gamma, the map is the constant map to 1. But this is very artificial one, and I have no good application of this algorithm. So if you can prove any well-known problem using this as a subroutine, then it would be good. And the second one is about the representation. So for the second part of the representation, there is some, we don't know for the case that we don't know the relation between K and L. So if we find, I believe this sentence, so if we find for K strictly larger than N, there is a ZPK graphic delta-matroid which is not representable over GFP to the L, then we can finish our theorem. We can complete our every gaps. Okay, we only have some examples, but very few. And yeah, thank you.
Right. Any questions?
there some result between some gamma 1 graphic delta-matroid and gamma 2 graphic delta-matroid? So, for example, such as G6 graphic delta-matroid implies G4 delta-matroid or something like that.
Of course, if there is a subgroup relation, then yeah, of course, but trivial, but for non-trivial case, I don't know. But I believe that if there is no subgroup relation between Z1 and Z2, then I think there is some example that this is Z1, but this is not Z2. I mean, not G1, but not G2. Gamma 1 and gamma 1. Here, or maybe quotient relation gives any. I don't know. But this is abelian, so quotient is also subgroup. Like, is it right? I don't know.
Potentially, like if something is gamma 1 graphic as well as gamma 2 graphic, then we may expect to have something like a regular delta-matroid. Yeah, that's a good question.
Yeah, maybe comparing Z2 and Z3 is very interesting, I think. I mean, Z2 graphic and Z3 graphic. No, Z2, we already know that even, so something other, Z3 or Z4. Sorry.
So, do you know anything about representability of like Z graphic delta-matroids?
Z.
So like infinite group?
Oh. I have no idea, but
So could it, in theory, be that that all Z graphic delta-matroids are representable over some field?
Yeah.
Or are there already counterexamples to that?
We don't have examples.
No.
I have no idea. Maybe not.
I mean, if you have delta-matroid which is not representable over any field, then that could be the counterexample.
Right. Sure.
But for the Z graphic, I don't know.
Can we say some representability for that P to the K graphic metric? I mean, not K power of the set P, but that
you mean
sub PK.
this?
Yeah. Can we say something representability of that delta graphic?
So even for this graphic delta-matroid, there is a this graphic delta-matroid which is not representable over some any field. For any given field, there is a ZPK graphic delta-matroid which is not representable over the given field F.
Yeah. Is there any?
So yeah, so this is just what this result saying. I mean, for the if we have finite, not this way. I'm a little confused, but we actually proved that for any field F. For any, I remember that we proved that for any field F, there is a ZPK graphic delta-matroid which is not representable for the field F. So the field the gamma must be this form.
Okay. Thanks.
Any other questions?
And
some comment is what I only check is about this is when P is 2 and K is 2 and L is 1, then there is some counterexample. So not this, but we don't know for the general case. P is 3 and K is 2, or P is 5 or K is 2, we don't know.
Counter example means that here
there is a gamma graphic delta matroid representative. I mean, there is a Z 2D graphic delta matroid representative over not representative. Yeah, I'm sorry. So there exists the Z2D2 graphic delta matroid not representable over the binary field. So here order is 2 to the 1. But if we replace this as a P, still I don't know.
Any other question? I think the speaker again.